Welcome to the podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to talk about Newton's universal law of gravitation.
Oh, another Newton's laws.
Yeah.
So there's not just three.
Welcome to the podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to talk about Newton's universal law of gravitation. I didn't know there was a fourth one.
Isn't there a fifth, too?
He talked about a lot of things. But really, this is what Newton was searching for. He wasn't trying to talk about apples falling from trees. He was, of course, trying to figure out why the moon went around the Earth, and why the Earth went around the sun, and the other planets went around the sun, and so forth. And so really, this, if you had the opportunity to talk to Isaac Newton, he would tell you that this was one of his greatest accomplishments, because no one else had been able to do this up until this point. And so you guys did some investigating where you discovered parts of Newton's universal law of gravitation, and then you were expected to put the whole picture together. So we're going to help in the building of that picture today. One of the things we're going to talk about, just to introduce it first, is the idea of a field. And I should write a force field. That's a somewhat controversial idea because we've all seen too much Star Trek and Star Wars.
Right.
We're going to talk about the inverse square law. That's important. We're going to talk about the concept of universal, meaning that, of course, it applies to all.
Everything in the universe.
Yeah. So the first thing we're going to talk about is the gravitational field. And up until this point, we've talked about gravity. We've expressed how important gravity is to us, specifically that the acceleration due to gravity is 9.81 meters per second squared. But what we really haven't gotten into is that gravity is what's called a field force, okay? Which means no contact necessary. We know this because if you were to let go of a stapler, the stapler is not touching the Earth, but it will fall to the Earth because the Earth's gravitational force will grab onto it and pull it down. So the Earth, like all objects, has mass. And any object that has mass has gravity. And we'll talk about any object, but we like to talk about the Earth because the Earth is huge. And everything that we see and everything that we observe is influenced, of course, by
This large mass.
this large thing of the Earth and its enormous mass. And so, what am I drawing here?
Field lines.
I'm drawing field lines.
So if I drop a penny, just like we did in class, if I drop a penny, it goes straight down. And if I'm in China, it goes straight down toward the center of mass.
Towards the center of mass, towards the center of the Earth. And the Earth is the biggest thing around us. So as far as most of us are concerned, the only thing that has gravity is, of course,
The Earth.
the Earth. But that is, in fact, not true. The reason why we notice only the Earth's gravitational pull is because we're so close to it. Whether you're aware of it or not, the moon's gravitational pull is affecting us every day.
Twice a day.
Twice a day in the form of
Tides.
the tides.
We don't notice it again because we don't have a large body of water near us, but even the tides, the moon even affects Lake Michigan.
Right. And it does affect the water level as it rises and it drops and etc. And it was Newton, of course, that was one of his great verifications, that it wasn't just the Earth that had gravity, it was the moon. We are, of course, influenced by the sun's gravitational pull because we go around the sun.
Correct.
All right? So this whole concept of field forces, no contact needed. Anywhere that you are within the field lines of an object means that the gravity of that object will influence the motion, okay, of anything near it. The closer the lines are together, okay, the more influence it has. So close lines equals more influence.
So therefore, that's the reason that gravity is what it is near the surface, and where gravity, things from the moon don't fall to the Earth with the same speed as things that are here.
Right. Because the moon then has its own gravitational field lines and things fall to it, but at a much slower rate because it has a much tinier mass.
Correct. So these gravitational lines are because of the mass, so that tells me that even something small like a bowling ball must have a gravitational field, but it must be overwhelmed by this large gravitational field of the Earth.
That is correct. And we talked about this a little bit when we introduced Newton's third law, that if an object, if the Earth is pulling an object towards it, the object is pulling the Earth towards it as well.
Correct.
So that's because of the field lines of, say, the bowling ball versus the Earth. You can't measure it, you can't see it. You could probably calculate it if you like zeros.
So this is a third law tells you that the force of the Earth on something is equal and opposite to the force of the other. So we had this discussion. I don't know if we did it in a podcast or something. So if all the people in China got up on a chair and they all jumped off, are they landing on the Earth, or is the Earth being pulled toward them?
Yes.
And the answer is yes.
Yeah, right. Both, of course, is true. Now, so if you have an object in space that's going around the Earth, it's a pretty decent space shuttle there.
Mm-hmm.
There's still gravity between the space shuttle and the Earth, of course, but it's not as noticeable because these field lines are spread out the farther you get away. If you're on top of a mountain, okay, the value of gravity is a little less there because the field lines are a little more separated there than they are when you're on the surface of the Earth. So that's another important thing, of course, to think about. Gravity's still present, but the farther you get away from that object, the less influence gravity will have because of the distance, which brings us right into the inverse square law. And what Newton discovered, and hopefully you got to this equation or some version of it, is that in order for there to be a gravitational force, there must be two objects, both having mass. There is some measurable distance between them, and that distance is squared in the denominator, hence inverse square right there.
Right on.
What Newton also discovered was this gravitational constant. It's a capital G. It's not a lowercase g. This is not 9.81. This is an awful number. It is 6.67 times 10 to the negative 11th. There are some units for it that I can never remember. It is a Newton meter squared divided by a kilogram squared. The units balance out so that you get newtons on the left side of the equation. So as you move away, you should have created this graph that showed, that showed that the acceleration due to gravity, I'm going to call it a sub g, is related to the distance like this, which of course is an inverse squared relationship. So at the Earth's surface, the value is at a nice, convenient 9.81.
Correct.
Okay? As you climb Mount Everest, it drops a little bit. As you leave the Earth's atmosphere, it drops a little bit. As you get to the moon, okay, the gravitational pull of the Earth is really insignificant, and then the gravitational pull of the moon takes over.
Right.
So that's what inverse squared means. I took this class in college where we talked about the importance of squared. Well, it's exactly inverse squared. It's not inverse to the power of 2.01. It's not inverse to the power of 1.99. It was a really fascinating discussion that how these numbers of 1, 2, 3 line up. And that's for another class and another day, but it does give you something to think about. And then the last point we wanted to talk about was that it is, in fact, universal. This is really important. Newton was in search of a scientific principle that explained the moon, the earth, the sun, the planets, those items. He knew that he just couldn't come up with an explanation for Earth, or Halley's Comet, or the moon. He knew that he had to come up with something that explained it all. And I think at first, if I remember correctly, he was interested in just explaining large planetary objects. But he realized that that explanation would be faulty because someone would come along and ask, well, what about this apple? What about this cannonball? Etc., etc. He knew that it had to be universal. So, gravity is a fundamental force. Now, in Newton's time, this was the only fundamental force that people knew about. And as far as most human beings are concerned, it's the only one that actually matters.
Well, it's the only one we deal with on a second-to-second basis,
Right.
too.
But there are four of them.
Right.
There's the electromagnetic force, which
Right.
we'll study. There's the weak nuclear force, which we'll talk about. And there's the strong nuclear force, which we'll also talk about. But we'll spend the majority of our time on gravity.
Which is really the weakest.
Yeah.
One of the weakest, for sure.
Because we overcome it all the time.
Right.
I'm going to get up out of this chair.
Stand up.
We walk
Walk.
upstairs.
Yep.
We run. We watch people slam dunk basketballs.
And the Earth is huge. So
compared
we're
to us.
overcoming the force of the Earth, which is huge, and we do it all the time.
So gravity is one of the four fundamental forces. It is weak. Okay? Now I say that, but it is really, really weak. It's, say compared to the force of gravity on Jupiter, which is a massive object and has a much larger gravitational pull, or the sun, or a whole host of other objects. But anyway, Newton figured out that this, in fact, had to apply to the stapler. It had to apply to the chair that you would sit in, etc. So that means that all objects, regardless of their mass, how big or tiny or in between the object was, would have field lines that would point towards it. And tiny objects would have a few field lines. And big objects would have lots of them, and they would be dense. And
Yeah, it's interesting to think about the fact that, like I said, the bowling ball actually has gravity. You have gravity.
Right. So theoretically, there are people that think that the universe revolves around them, and I suppose if they were in the middle of space and they had a paperclip, they could make that paperclip orbit them and satisfy their desire to be the center of it all. All kidding aside, Newton realized that these rules about inverse squared and field lines and thinking about this stuff had to apply to everything. It had to be a universal law. Here was Newton's problem. First of all, he was not an experimentalist. We talked about this before. Newton was a thinker. When he thought it, he knew it was right. He wrote it down, and that was it for Newton. He didn't care about anything else. But someone had to come along and prove this. And the guy's name was Henry Cavendish. And his experiment is explained very nicely on page 386, where he invents this machine, where he has some orbs, as he likes, as they call them, and these orbs are connected with a rod and hanging from a string, and they're in relationship to other hanging larger orbs. And he was able to, he was able to induce some movement by moving some orbs and not others, and watch them pull, because what he knew that Newton knew was gravity is attractive. And so that if he can move these things in just the right way, he could show that even tiny objects, like as light as 10 pounds or 3 kilograms, actually have some gravity versus 1 kilogram and so on. So Cavendish was able to verify Newton's work.
I think it's interesting that it took 100 years to come up with an experiment to prove the man was right.
Yeah. And that's how far ahead of his time Isaac Newton was, and everyone played catch up to this guy for 300 years, of course, until Albert Einstein came along. So that's the universal law of gravitation. How does that affect roller coasters? Roller coasters on the moon would be boring because of its low gravitational pull. roller coasters on the planet of Jupiter, assuming that it has something that you could build a roller coaster on, would kill you.
Right.
Because of its value of gravity. So we talk about these things. This is a big idea, but it can apply. What if G was different? Could you go faster, slower, etc.? So I believe that covers a very complex topic. Signing off, this is Mr. White.
And Mr. Sadler.